Two particles can whisper to each other across the emptiness of a galaxy. This is quantum entanglement, the universe's strangest and most baffling phenomenon. By the end of this journey, you will have explored 30 radically different explanations for how this magic trick of physics could possibly be real. We will see how this single mystery threatens our understanding of space and time, and even suggests that reality itself might be woven from a web of invisible connections. Is our universe a cosmic hologram, or are we living inside a vast quantum computer? Which idea will make you question everything you thought you knew about how the world works? The first and most enduring explanation comes from the very heart of quantum theory itself. It is called the Copenhagen interpretation, named for the city where its architects Niels Bohr and Werner Heisenberg did their groundbreaking work. This is the story many of us first hear, the standard version taught in textbooks. Its central idea is disarmingly simple yet profoundly unsettling. According to this view, a particle like an electron does not have a definite property like a specific spin direction until the moment you look at it. Before measurement, it exists in a ghostly state of all possibilities at once, described only by a mathematical entity called the wave function. This wave function is not a physical thing you can touch. It is a cloud of potential, a list of probabilities for what you might find. Entanglement, then, is not a physical signal traveling between particles. It is a feature of this shared wave function. Imagine two coins spinning in perfect unison inside a sealed black box. According to the rules, each coin is simultaneously both heads and tails. This is their entangled state. The moment you open the box and see one coin land as heads, the wave function for the entire two-coin system instantly collapses. The other coin, no matter where it is in the universe, is now definitively tails. There was no message sent. The information was already embedded in the shared mathematical description of their reality. This is what Albert Einstein famously called spooky action at a distance. He hated the idea, believing it implied faster-than-light communication, which his theory of relativity forbade. For the Copenhagen camp, however, there is no spooky action, only a sudden update of our knowledge about a system that was never fully real until we looked. The power of this interpretation lies in its stark simplicity. It draws a clear, if mysterious, line. On one side is the quantum world of probabilities and potential. On the other side is the classical world of definite facts brought into being by an act of observation. But who or what qualifies as an observer? Is it a human scientist, a camera, a cat in a box? The Copenhagen interpretation is famously silent on this, treating the measurement process as a fundamental, unexplained boundary. It does not try to tell us what reality is doing when we are not looking. It only provides a flawless recipe for predicting what we will see when we do. For this pragmatic reason, it remains the working foundation for countless experiments and technologies. Yet, by accepting this strange duality as the final answer, it leaves us staring into the deepest mystery of all. What is truly happening in that instant of collapse, in the silence between the question and the answer? Einstein's spooky action demands a better answer, and one theory offers a breathtakingly radical solution. It suggests that the wave function never collapses at all. Instead, every single possible outcome of a quantum event actually happens, just in a different, newly created branch of reality. This is the many worlds interpretation. Picture our two entangled particles spinning coins in a box. In the Copenhagen view, opening the box forces one definite outcome. In the many worlds view, opening the box causes the entire universe to split. In one new branch, you see the left coin as heads and the right as tails. In another, brand new, equally real branch, you see the left coin as tails and the right as heads. Both views are real, both outcomes occur, so what we call quantum entanglement is not a mysterious signal. It is simply a correlation preserved across these branching realities. When you measure your particle here in this branch, its partner particle is already in the corresponding state in this same branch. The correlation was baked into the universe at the moment of entanglement, and it simply carries forward as reality continually divides. This idea has a powerful, elegant appeal. It completely eliminates the need for a magical, unexplained collapse of the wave function. The mathematics flows smoothly without that jarring break. There is no spooky action because nothing is communicating across space. Every possible result simply exists somewhere. The price for this elegant solution, of course, is almost beyond comprehension. It means that for every quantum event, every choice, every random fluctuation, the universe is constantly and endlessly splitting. Right now, uncountable versions of you are living out every possible variation of your life in parallel worlds. This interpretation turns the universe from a single, unfolding story into a vast, ever-growing library containing every story that could possibly be written. It solves the mystery of entanglement by making the universe infinitely bigger, and in doing so, asks us to let go of the idea that our reality is the only one that is real. But the idea of infinite branching universes is not the only way to escape the ghostly collapse. There exists a path that leads in the opposite direction, back toward a universe that is solid, real, and predictable. This is the pilot wave theory, also known as the de Broglie-Bohm theory, and it offers a stunningly different vision. It dares to suggest that Einstein was right to be skeptical of pure randomness and that particles are not probability clouds. They are tiny, definite objects with real positions, following real paths through space, just like a boat on the ocean. The quantum weirdness does not come from the particles themselves, but from the ocean they sail upon. In this theory, every particle is accompanied by an invisible, guiding wave. Think of this pilot wave as a complex pattern of ripples spreading throughout the universe, a kind of quantum weather map. The particle does not exist in many places at once. It has one specific location, but it is relentlessly pushed and steered by this invisible wave. Where the wave is strong, the particle is likely to be found. This is the hidden variable, a secret layer of reality that determines exactly what happens. Entanglement, then, becomes a dramatic dance choreographed by this hidden sea. When two particles become entangled, their pilot waves merge into a single, unified rippling field. The particles themselves are separate, but they are both surfing the same wave. A disturbance to one particle instantly changes the shape of the entire guiding wave, which in turn immediately adjusts the path of the other particle, no matter the distance. This is the non-local connection, an influence that travels faster than light. Yet, and this is the crucial twist, this influence cannot be used to send a message. You cannot control the specific kick you give to your particle in a way that encodes information. The outcome for the other particle remains correlated, but it is still random from your perspective because you cannot see or control the detailed state of the hidden pilot wave. It is like two buoys bobbing on a stormy sea, connected not by a rope but by the entire ocean itself. If a giant wave hits one buoy, the sea's entire pattern changes, affecting the second buoy instantly. But you, standing on shore, cannot create a specific wave pattern to make the second buoy spell out your name. The connection is real and instantaneous, but it is not a telephone line. This theory restores a comforting determinism to the quantum world. If you could know the exact state of every particle and its pilot wave, you could, in principle, predict the future with perfect accuracy. There is no fundamental randomness, only hidden complexity. It paints a universe that is deeply interconnected in a way that defies our classical intuition about space, yet remains stubbornly, tangibly real. It is a universe with secrets, but not with ghosts. Hidden variables and branching universes both try to solve the measurement problem by changing what we think is real. But what if the problem is not in our interpretation, but in the mathematics itself? What if the wave function's collapse is not a ghostly mystery or a cosmic split, but a literal physical event like a stick snapping under its own weight? This is the bold claim of objective collapse theories. They propose that the wave function is unstable. Left to its own devices, it will spontaneously and randomly collapse all by itself. The most famous of these ideas is the JRW theory, named for its creators Garrodi, Rimini, and Weber. Their proposal adds a single, tiny tweak to the equations of quantum mechanics. They suggest that every particle has a very small, but non-zero, probability of spontaneously localizing at any given moment. For a single electron, this chance is so minuscule that it might only happen once in 100 million years. It would spend almost its entire life as a blurry cloud of probability. But here is the key. Large objects like a cat or a measuring device are made of trillions upon trillions of particles. In such a massive collection, the probability that at least one particle will undergo this spontaneous collapse becomes overwhelming, happening many times per second. And because the particles are all entangled within the object, the collapse of one triggers the collapse of them all, instantly crystallizing the entire macroscopic thing into a definite state. In this view, there is no special role for a conscious observer. Measurement happens because of size. The quantum world of fuzzy probabilities is inherently fragile, and when enough matter is gathered together, it inevitably and physically shatters into classical certainty. So how does this explain our two entangled particles? Imagine they are created together and fly apart. Their shared wave function describes all the possible correlated states. According to GRW, this delicate, spread-out quantum state simply cannot survive for long in the real world. At some random moment, triggered by the spontaneous localization of just one particle in the system, the entire entangled wave function will objectively collapse. At that instant, before any human looks, the particles snap into definite, correlated states. The correlation was always there in the mathematics, waiting. The collapse just makes it physically real. When a scientist later checks one particle, they are merely discovering a fact that was already set in stone by an earlier, objective physical process. This elegantly bridges the quantum and classical worlds. It draws the line not at consciousness but at scale. It says the universe itself has two sets of rules. One for the tiny, fleeting domain of particles where probability reigns until mass accumulates, and another for the world of tables, planets, and cats, which are too heavy to stay in quantum limbo. Reality, according to this theory, is constantly resolving itself out of a haze of possibilities, not because we are looking, but because it simply cannot help it. But what if all these theories are asking the wrong question entirely? What if the wave function is not a description of the world, but a description of your mind? This is the startling perspective of quantum Bayesianism, or cubism for short. It takes the mystery of quantum mechanics and turns it inward, suggesting the strangeness is not out there in the universe, but in the very nature of how we understand and interact with it. In this view, a quantum state, that mathematical cloud of probability, does not represent an objective particle. It represents a personal belief, a degree of confidence. It is a gambler's odds sheet, not a map of reality. When you say an electron has a 50% chance of spinning up, you are not describing a fuzzy electron. You are describing your own incomplete knowledge and your best bet for what will happen when you place your measurement. So what then is entanglement in this deeply personal universe? It is not a physical link between distant objects. It is a correlation in the beliefs of different observers. Let us return to our two coins in the box. For a cubist, before anyone looks, there is no single true state of the coins. There is only your personal quantum assignment, your betting odds, which encode the fact that if you see heads here, you must bet on tails over there. Now, a second scientist on a distant planet opens the other box. They make a measurement and update their own personal belief state instantly. From your perspective, when you later learn their result, you must dramatically update your own betting sheet to be consistent. That sudden, jarring update of your information feels like spooky action, but no faster than light influence traveled through space. Only a message constrained by light speed eventually informed you that your old betting odds were obsolete. The spookiness is the shock of changing your mind, not a signal changing the world. This framework completely dissolves the measurement problem. The wave function does not collapse because the world changes. It collapses because you, the agent, have gained new information and must revise your expectations. The universe does not split, and no hidden variables guide particles. There is just a single, concrete reality, and we, as limited observers within it, are constantly making personal, probabilistic guesses about it. Entanglement, then, becomes a powerful protocol for coordinating beliefs between agents who have shared a common quantum experience. It is the rulebook that tells us how our individual stories about the universe must remain consistent with each other. Cubism makes quantum mechanics a theory not about what is, but about what to expect. It is a guide for decision-making in a world that is fundamentally unpredictable to us. This places the mystery squarely in the human condition, in the gap between our finite perspective and the vast, silent reality that exists whether we bet on it or not. The magic is not in the particles, it is in the profound challenge of being a conscious agent trying to make sense of a cosmos that does not reveal its secrets easily. The search for a single, true reality may itself be the source of our confusion. What if every observer, every measuring device, every piece of the universe carries its own equally valid version of events? This is the radical proposal of relational quantum mechanics, an idea that suggests properties like position or spin are not inherent to an object, but exist only in the relationship between that object and something else observing it. There is no grand, absolute stage on which the quantum drama plays out. Instead, reality is a vast network of individual perspectives, each describing the interactions they have with the world. In this view, an electron does not have a spin up or spin down in isolation. It only has a spin relative to you or to a detector or to another particle. Entanglement, then, is not a mysterious link between two things. It is a perfect correlation within a specific relationship. Let us return to our two particles flying apart. For you, the observer who created them, they are described by a single, entangled quantum state. That is your relational truth. But now imagine a second scientist far away who has never interacted with your lab. From her perspective, completely independent of yours, she might encounter one of these particles as just an ordinary, unremarkable object with a definite spin. She has no knowledge of its entangled partner, so in her relational account of reality, it is not entangled at all. Both of your descriptions are correct within your own frame of reference. The paradox of spooky action dissolves because there is no single, universal moment of collapse that everyone must agree on. When you measure your particle, you update the relationship between you and the entire two-particle system. For you, the correlation becomes a definite fact. For the distant scientist who is not part of that interaction, nothing spooky happened. She simply continues with her own description, which will only later need to be reconciled with yours when you finally compare notes. It is as if two people are writing separate chapters of the same book from different points of view. Their chapters can contain different descriptions of the same event, yet both are valid parts of the overall story. The universe, in this theory, is not a collection of things with fixed properties. It is a tapestry of constantly shifting perspectives, where every interaction weaves a new thread of relational fact. This means there is no bird's eye view of reality, no God's perspective from which everything is simultaneously definite. We are all participants, not spectators, and the quantum world reflects the simple, profound truth that what we see depends entirely on who we are and how we are connected to everything else. A universe of shifting perspectives might still feel too abstract, but one theory offers a shockingly concrete mechanism for the quantum link. The transactional interpretation dares to propose that the handshake of entanglement is not just a correlation, but a literal deal struck across time itself. Its architect, physicist John Cramer, suggested we take the mathematics of quantum theory at face value. The equations show waves that can travel both forward and backward in time. What if we stop seeing this as a mathematical quirk and start seeing it as a blueprint for reality? In this view, every quantum event, like measuring a particle, begins with an offer. Imagine you have a detector set up to catch an electron. According to this theory, the detector first sends out a subtle invitation wave backward through time. This is a retarded wave moving from the present into the past. It travels back to the moment the electron was created and whispers, "I am here and ready to receive you." The electron at its origin then responds by sending a confirmation wave forward through time. This is an advanced wave. The transaction is completed when these two waves, one from the future and one from the past, perfectly match up and reinforce each other. Only then does the electron actually appear at the detector, its path and properties now settled. It is as if reality is a marketplace where deals are negotiated across time, and particles only manifest when a bargain is struck. Now apply this breathtaking idea to our two entangled particles. At the moment they are created, their future is a fog of possibilities. But scattered across spacetime are potential detectors, observers, or any system that will eventually interact with them. Each of these future points sends its own offer waves backward in time. The entangled pair at the source receives a symphony of these overlapping invitations from all their possible futures. The transaction that ultimately gets confirmed is the one that satisfies all the correlations at once. So when you decide to measure the spin of particle A, your detector's offer wave traveled back to the birth of the pair. That backward in time signal helped negotiate the deal that gave particle A its specific spin, and simultaneously locked in the correlated spin for its partner, particle B, to satisfy the original entanglement. The spooky action across space is explained by a negotiation that was finalized in the shared past of the particles. There was no faster than light signal between them now. The connection was cemented long ago, when waves from their mutual futures converged at their point of origin and sealed their fates in a single, time-symmetric handshake. This gives us a startlingly physical picture of non-locality. The particles are connected not by a mysterious invisible thread in space, but by a closed loop in spacetime, a transaction whose terms were written with input from both their past and their future. It paints the universe as an arena where causes and effects can intertwine, where the future might gently tug on the past to bring about the definite world we experience in the present. There is a theory so unsettling that it resolves the quantum mystery by questioning a foundation of human experience itself. This is superdeterminism, and it proposes a universe of such perfect, unbroken causality that even our thoughts and choices are part of its clockwork. It dares to ask, what if the spooky correlations of entanglement are not due to strange signals or branching worlds, but because everything, including the scientist running the experiment, was preordained to align from the very first moment of the cosmos? Imagine the classic entanglement test. Two particles fly to opposite sides of the lab, and a researcher chooses at random which property to measure. The particles always match in a way that defies local explanation. Superdeterminism offers a brutal simplicity. There is no faster than light influence because there is no free choice in the experiment. The researcher's decision to measure spin up or down is not a random, independent event. It is the inevitable result of a chain of causes stretching back to the Big Bang. That chain is intricately linked to the chain that produced the entangled particles themselves. In this view, the universe is a single, monolithic block of predetermined events. The correlation between particle A and particle B is not established when they are measured. It was written into the fabric of reality 13.8 billion years ago, along with the exact neural firings that would lead a specific human to press a specific button at a specific nanosecond. The experiment's outcome feels mysteriously coordinated because the experimenter and the particles are all dancing to the same ancient song. This idea utterly eliminates the need for spooky action. There is no signal between the particles because their states and the measurement settings were never independent variables to begin with. They are all different notes in a symphony that was composed in its entirety at the dawn of time. The perfect match is no more mysterious than the fact that the first and last movements of a pre-recorded symphony fit together perfectly. They were created as a single unit. For most physicists, this is a bitter pill to swallow. It does not just describe a deterministic universe, it demands a super-deterministic one, where the very notion of free will is an illusion. Our sense of making independent choices is a compelling story generated by the deterministic workings of our brains, part of the script. Critics argue this makes science itself impossible. Science relies on the assumption that an experimenter can set up a test freely, independent of the system being studied. If superdeterminism is true, that assumption is false, and every experiment is merely revealing a correlation predetermined at the birth of the cosmos, not testing a fundamental law. Yet its proponents see it as the ultimate parsimonious solution. It requires no new particles, no collapsing waves, no parallel universes. It simply asserts that the universe is a single, seamless, predetermined whole, and the eerie magic of quantum connection is just our limited perspective, slowly reading a story that was finished long, long ago. The idea of a predetermined cosmos is a profound shock to our sense of agency, but another theory delivers a shock to our perception of reality itself. It suggests that the solid, three-dimensional space we inhabit, with its depth and distance, is a magnificent illusion. This is the holographic principle, and it offers perhaps the most profound connection yet between quantum entanglement and the very fabric of the cosmos. The theory begins with a startling claim about black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon. This was bizarre. It implied that all the information needed to describe everything that ever fell into the black hole could be perfectly encoded on its two-dimensional boundary, like a cosmic movie projected onto a spherical screen. The three-dimensional interior, the bulk of the black hole, would then be a holographic projection of that data. Extrapolating this radical notion, some physicists like Leonard Susskind proposed that our entire universe might operate on the same principle. The three-dimensional space around you, with all its stars, planets, and people, could be a hologram. The true, fundamental reality is a distant, two-dimensional surface at the cosmic horizon, where information is stored in tiny, vibrating Planck-scale pixels. If this sounds like science fiction, consider its breathtaking implication for entanglement. What if the threads of quantum entanglement that stitch particles together are the very threads that weave the illusion of space? In this holographic view, two particles that are entangled in our three-dimensional world are not actually connected by a mysterious force through empty space. Instead, their connection is fundamental, written directly into the code on the two-dimensional boundary. Their entanglement is a primitive fact, the experience of empty space between them, the geometry of distance itself, emerges from the complexity and density of these quantum links. Think of a three-dimensional image on your credit card. It looks deep and solid, but it is generated entirely from flat, microscopic ridges on the card's surface. In the cosmic hologram, the ridges are entangled quantum bits. The more entanglement there is between regions on the boundary, the smoother and more continuous the spacetime that emerges in the projected 3D world. If entanglement is severed, the fabric of spacetime itself could fray, becoming grainy or even disintegrating. This turns our understanding of the universe inside out. We are used to thinking of space as a static stage and entanglement as a strange phenomenon that happens upon it. The holographic principle suggests the opposite. Entanglement is the primary ingredient, and space is the secondary consequence, a kind of useful mirage that emerges from a vast, interconnected quantum network. It proposes that every centimeter of distance you perceive, every gravitational pull you feel, is not a fundamental property of reality, but a story told by countless entangled threads on the edge of everything. So the next time you feel the vast emptiness between stars, remember that emptiness may be the richest thing of all, a tapestry of invisible quantum connections so dense and intricate that it paints the entire picture of our physical world. The hologram theory suggests space is woven from entanglement, but what if those threads are not just metaphors but literal tunnels? This brings us to one of the most thrilling and geometrically beautiful ideas in modern physics, a conjecture so elegant it is often written as a simple equation, ER equals EPR. On one side, EPR stands for Einstein, Podolsky, and Rosen, the authors of the famous paper highlighting the spooky paradox of entanglement. On the other side, ER stands for Einstein and Rosen, who later collaborated on a theory of bridges through spacetime known today as wormholes. The conjecture, championed by physicists like Leonard Susskind and Juan Maldacena, proposes that these two concepts discovered by the same man decades apart are not just related. They are the same thing. An entangled pair of particles, according to this radical view, are not communicating faster than light across empty space. They are connected by a microscopic wormhole, a tunnel in the fabric of spacetime so tiny it is governed by quantum laws. This wormhole is not a traversable passage you could fly a ship through. It is a ghostly quantum link, often called an Einstein-Rosen bridge. In this picture, when you create two entangled particles, you are not just linking their quantum states. You are, in essence, pinching the fabric of reality and stitching it together with an invisible thread of spacetime itself. The spooky action is no longer action at a distance. It is action through a shortcut. Imagine two friends living in cities far apart. If they can only communicate by mailing letters across the continent, their connection seems slow and distant. But if a secret private subway tunnel existed directly between their basements, they could pass notes instantly. The outside world sees them as separate, but their private connection makes them neighbors. In the ER equals EPR proposal, entangled particles are like those friends. The vast space between them is an illusion from our classical perspective. At the quantum gravitational level, they share a basement, a tiny bridge that bypasses the apparent separation. This provides a stunning geometric explanation for non-locality. The quantum information does not need to race across the void. It simply takes a hidden back door, a cosmic alleyway that folds the map of the universe. The implications for unifying gravity and quantum mechanics are profound. Gravity, in Einstein's theory, is the curvature of spacetime. Quantum mechanics is the rules of the very small. They have famously refused to fit together, but here, the quintessential quantum phenomenon, entanglement, is described using the geometry of spacetime, the language of gravity. It suggests that the weirdest feature of the quantum world might be the very ingredient that stitches spacetime together. The wormholes are too small and unstable for matter, but they are perfect conduits for quantum information, weaving the correlations that might underpin the structure of everything. This idea turns the mystery inside out. We have been asking how particles influence each other across space. ER equals EPR answers that they were never truly apart to begin with. Their connection is not magic, it is architecture written into the hidden blueprints of reality. It hints that when we finally peer into the heart of a black hole or the first instant of the Big Bang, we might not find a singularity of infinite density, but a dense, tangled web of these quantum bridges, the fundamental stitches in the fabric of the cosmos. Our journey through quantum bridges now takes us to the edge of the abyss, to the most extreme laboratories the universe provides. Black holes are not just cosmic vacuum cleaners. They are the ultimate paradox machines, and at the heart of their deepest mystery lies entanglement. The story begins with Stephen Hawking's revolutionary discovery in the 1970s. He showed that black holes are not truly black. Due to quantum effects at their event horizons, they slowly evaporate, emitting a faint glow of particles now called Hawking radiation. This radiation carries away energy, causing the black hole to shrink and eventually vanish. But this beautiful idea created a catastrophic problem known as the information paradox. In quantum mechanics, information is never destroyed. The exact quantum state of every particle that falls into a black hole should, in principle, be preserved forever, even if scrambled beyond recognition. Yet if the black hole evaporates completely, leaving behind only generic, random Hawking radiation, that information seems to be irretrievably lost. It vanishes from our universe, violating a sacred quantum law. For decades, physicists wrestled with this. The leading solution hinges on a delicate quantum handshake. When a pair of virtual particles pops into existence at the very edge of the event horizon, one falls in while the other escapes as Hawking radiation. According to the rules, these two particles must be entangled. The particle inside carries information about what fell into the black hole, while its entangled partner outside carries that same information away in the radiation. As the black hole evaporates over eons, the hope was that all the original information would eventually be encoded in the total pattern of outgoing radiation, meticulously transferred via these countless entangled pairs. The paradox seemed solved until it created an even more violent contradiction. Fast forward to the final stages of evaporation. The black hole is now tiny, and the Hawking radiation it emitted long ago is far away in space. That old radiation must still be entangled with the new radiation being emitted now from the shrinking remnant. But here lies the crisis. A fundamental rule of quantum mechanics says that entanglement cannot be shared freely, a principle called monogamy. A particle can be deeply entangled with one partner, but not with two. The new radiation must be entangled with the old radiation to preserve information, but it must also be entangled with its partner that fell inside the black hole. This is an impossible love triangle. To resolve it, something has to give. In 2012, a team of physicists proposed a shocking answer. The entanglement between the infalling particle and its outgoing partner must violently sever at the event horizon. This sudden quantum divorce would release an immense amount of energy, transforming the event horizon into a blazing wall of fire, an incandescent barrier that would incinerate anything trying to cross. This is the infamous firewall paradox. It presents a brutal choice. Either we abandon the principle that information is preserved, or we abandon Einstein's cherished principle of equivalence, which states that an astronaut falling through the event horizon of a large black hole should feel nothing special, no drama, just the smooth fabric of spacetime. A firewall is very dramatic indeed. The existence of a firewall forces us to radically rethink locality, the idea that objects are only influenced by their immediate surroundings. It suggests that the event horizon, a location defined by gravity, is acutely sensitive to quantum information that has fled far across the universe in the form of old Hawking radiation. The fate of an astronaut at the horizon depends on the state of particles emitted billions of years ago. This is non-locality on a cosmic, terrifying scale. In wrestling with this, physicists are realizing that black holes are not just objects in space. They are dynamic knots of spacetime geometry woven from quantum entanglement. Resolving the firewall paradox may require us to see the event horizon not as a sharp boundary, but as a fuzzy, fluctuating quantum structure where entanglement connections are constantly being traded and transferred. It makes black holes the ultimate testing grounds for theories of quantum gravity. places where the threads of entanglement either stitch reality together or, perhaps, reveal where the fabric truly begins to fray. The firewall crisis forces us to ask what entanglement truly is in the language of gravity. A remarkable answer comes from a theoretical framework so precise it is considered a mathematical proof of the holographic principle. This is the anti-de Sitter/conformal field theory correspondence, often called the most important discovery in string theory. It provides a concrete dictionary for translating between two seemingly alien worlds. On one side is a universe with gravity. This is the bulk, a warped, higher-dimensional space known as anti-de Sitter space, which acts like a cosmic basin with a distinct boundary. On the other side, living on that lower-dimensional boundary, is a quantum field theory without gravity at all, a bustling world of particles and forces described by conformal symmetry. The slash in the middle is an equal sign. The add/CFT correspondence states that these two descriptions are completely equivalent. They are not just similar. They are two different languages telling the exact same story. Every single phenomenon in the gravitational bulk, every star, every black hole, every ripple in spacetime, has a perfect translation into the complex interactions of quantum particles on the boundary. And crucially, the currency of this translation is information. Entanglement on the boundary becomes the very geometry of spacetime in the bulk. We can see this with a stunning calculation. Physicists can take a region on the boundary quantum field theory and compute its entanglement entropy, a precise measure of how quantum information is shared between that region and the rest of the boundary. When they then use the holographic dictionary to ask what this corresponds to in the gravitational bulk, the answer is breathtaking. The entanglement entropy of the boundary region is exactly proportional to the area of a minimal surface that extends from that region's edge into the bulk, like a soap film stretching across the interior. This is not an analogy, it is a mathematical identity. More entanglement on the boundary directly corresponds to a larger minimal surface area in the bulk geometry. This reveals the deep mechanical link. Spacetime is not a given stage. It is built piece by piece from the quantum entanglement between different parts of the boundary theory. If you were to reduce the entanglement between two regions on the boundary, the corresponding minimal surface in the bulk would shrink. In the extreme case, if you severed all entanglement, the geometric connection between the corresponding regions in the bulk would pinch off entirely, like a tunnel collapsing. This gives us a profound new lens on wormholes, that microscopic Einstein-Rosen bridge connecting two entangled particles. In the language of add/CFT, the bridge is the geometric manifestation in the bulk, while the entanglement is the fundamental data on the boundary. They are two sides of the same coin, described with perfect mathematical duality. This framework does more than just explain a mystery, it provides a powerful tool. Physicists can now take impossibly difficult questions about quantum gravity in a warped spacetime and translate them into more manageable questions about quantum particles on a flat boundary, solve them there, and then translate the answer back. It turns the deepest problem in physics into a complex but well-defined calculation about information. The correspondence solidifies a radical new ontology for the universe. Gravity is not a fundamental force, it is an emergent phenomenon, a collective consequence of vast numbers of quantum bits on a distant surface being intricately entangled. The three-dimensional world we experience, with its forces and matter, is a dynamic hologram, and the code that generates it is written in the language of quantum information and correlation. We are not living in the universe, we are living in its shadow, a projection so rich and consistent that it has convinced us of its own solidity for millennia. The hologram paints a picture, but where do the pixels themselves come from? If entanglement weaves the fabric of space, we must ask what the threads are made of. This leads us to a theory where the universe itself began not as a smooth expanse, but as a chaotic, tangled web of pure connection. imagine the cosmos in its first searing moment. There is no space as we know it, no distance, no up or down. Instead, there is only an immense buzzing network. Every node in this network is a fundamental quantum bit of information, a qubit. And every link between nodes is a bond of quantum entanglement. This is the vision of theories like quantum gravity. In this infant state, the universe is a complete graph. Every single qubit is directly entangled with every other qubit. It is a state of ultimate unity, but also of ultimate chaos. There is no notion of here versus there because everything is equally connected to everything else. Geometry in any sensible form does not exist. Then, as this fiery network begins to cool, something remarkable happens. The pattern of entanglement starts to change. Think of water freezing. In its liquid state, water molecules slide past each other in a disordered dance. As it cools, they begin to lock into a rigid, crystalline structure, the lattice of ice. In a similar cosmic freezing, the all-to-all entanglement of the hot early universe begins to crystallize. Most of the quantum links between distant qubits snap. Entanglement becomes localized, forming strong bonds only between nearest neighbors in the emerging network. As this happens, a structure begins to appear from the chaos. The pattern of which qubits remain entangled defines the very concept of proximity. Two qubits that stay strongly linked become neighbors in the new, emergent space. Those whose connection is severed become distant. From this selective pruning of quantum links, the dimensions of our reality slowly freeze out. The network organizes itself into a stable lattice, and from that lattice, the smooth, continuous fabric of space we perceive emerges as a large-scale approximation. Much like a television screen's smooth image emerges from the discrete pattern of its pixels. In this view, the three-dimensional space of our everyday life is not a fundamental stage. It is a phase of matter like ice or steam that the universe settled into as it cooled. The speed of light, that ultimate cosmic speed limit, may simply be the rate at which information can hop along this crystallized network of entangled links. Even the force of gravity could be a kind of elastic response when this quantum graph is stretched or deformed by mass. This transforms our understanding of entanglement from a strange phenomenon within space to the very substance of space itself. The empty void between stars is not empty at all. It is a highly ordered, low-energy state of this quantum network, humming with latent connections. When particles become entangled in experiments, we are not creating a new link in space. We are briefly exciting the underlying network, strengthening or rearranging the fundamental threads that are always there, stitching the void together. It suggests that if we could reheat the universe to its birth temperature, space as we know it would melt away, leaving only a seething, interconnected whole where every part instantly feels every other part. Our experience of separation is not the default state of the cosmos. It is the calm, crystalline order that emerged from a far more connected and far stranger quantum beginning. A crystalline network of quantum links gives us space, but how does it give us the stable, definite world we see around us? Why do we not witness chairs or cats in blurry superpositions, but only in one specific place? The answer may lie in a process of cosmic selection, where entanglement acts not as a mystery but as a judge. This is quantum Darwinism, a theory that frames our classical reality as the outcome of a fierce competition for survival in a quantum arena. At its heart is a simple, powerful question. When a quantum system meets the messy, complicated environment, which of its many possible states will endure? Imagine a single, delicate soap bubble floating in a storm. Most bubbles pop instantly, destroyed by the chaotic air currents, but a rare few with just the right size and thickness might survive long enough to be seen. In the quantum world, the storm is the environment, every stray photon, air molecule, and dust particle. A quantum object, like an electron, starts in a fragile superposition of many states. But as it inevitably bumps into the environment, it becomes entangled with countless particles around it. This is the key. Most entanglements are destructive. They decohere the system, rapidly scrambling and erasing the delicate quantum information. However, a special few quantum states are robust. They are the soap bubbles that can withstand the storm. These are called pointer states, and they have a unique property. When they interact with the environment, they do not get scrambled. Instead, they imprint copies of themselves onto the environment through entanglement. Think of a stone dropped into a pond. Most shapes you could carve onto that stone would be lost as it sinks, creating only messy ripples. But a perfectly spherical stone creates clean, concentric, and identical waves in every direction. That spherical shape is the pointer state. The water molecules become entangled with the stone, but they all tell the same, consistent story about its roundness. In quantum Darwinism, the environment is not an enemy that destroys quantum weirdness. It is a witness, a copying machine. A pointer state, like a specific position or a definite spin, becomes redundantly entangled with countless fragments of the environment. A photon bouncing off an object carries a copy of its location. A nearby air molecule does the same. Over trillions upon trillions of such interactions, the information about that pointer state is broadcast far and wide. This redundancy is what makes reality objective. You, I, and any other observer can each independently measure the environment in our own way by catching a few of those photons or molecules, and we will all agree on what we see. We all read the same story from different pages of the cosmic record. Entanglement, in this view, is the very mechanism of selection. It is the process that sifts through the infinite quantum possibilities and singles out the stable, classical facts that constitute our world. The states that survive are not chosen by a conscious observer. They are chosen by their fitness to be copied. They are the quantum shapes that can entangle with the environment without being destroyed by it. So our two mysterious particles, when measured, are not collapsing due to our gaze. Their interaction with the measuring device, itself a vast collection of environmental particles, forces them into pointer states. Those states then get redundantly copied into the device's components, and then into the light entering our eyes and into our neural pathways. The spooky correlation of their entanglement is simply a pre-established agreement that gets broadcast and amplified through this same copying process until it becomes an objective fact for anyone who cares to look. Quantum Darwinism tells us that the world we perceive is not the full quantum tapestry. It is only the tiny, robust fragment of that tapestry that has learned to multiply, to make countless copies of itself in the environment. We do not see quantum reality because we are not equipped to read the fragile, singular threads. We only see the bold, redundant patterns woven by entanglement, the stories so widely told that they become the consensus reality. Our classical world is not fundamental. It is the loudest, most persistent echo in a quantum chamber of whispers. But if reality is a consensus broadcast by the environment, who is listening? This question brings us to the most speculative and controversial theory of all, one that places the ultimate power of creation not in the cosmos but within ourselves. This is the conscious observer theory, the idea that the wave function collapses only when it is observed by a conscious mind. In this breathtaking view, the quantum world remains in a shimmering state of all possibilities until the moment it enters the awareness of a living, thinking being. Our two entangled particles would spin in an indefinite, correlated haze for eternity unless a conscious entity decides to look. The act of observation itself, the spark of awareness, is what forces the universe to choose one concrete reality from the infinite quantum menu. This idea finds its roots in the early days of quantum mechanics. Some of its founders, like John von Neumann and Eugene Wigner, wrestled with the measurement problem and asked where the chain of collapse finally ends. A detector is just a machine, and machines are made of quantum parts. So what causes its quantum state to resolve? they reason that the chain must terminate at the only thing that is definitively not a quantum system, consciousness itself. In this interpretation, entanglement is the ultimate secret, held in trust by the universe until a conscious mind unlocks it. The particles are not secretly communicating. They are waiting. When you, the observer, focus your attention on one particle, your consciousness collapses its state. But because the particles are described by a single, unified wave function, that collapse is not local. It is instantaneous and universal for that system. Your act of seeing here determines the state of its partner there, bringing both particles into definite existence simultaneously through the power of your awareness. Critics from mainstream physics are swift and severe. They point out the glaring circularity. If consciousness causes collapse, then what is consciousness, and how does it physically interact with atoms? The theory offers no mechanism, only a mysterious boundary. It also leads to bizarre paradoxes. Was the moon in a superposition of positions before the first conscious creature looked at it? Did galaxies float in quantum limbo until conscious life evolved to witness them? This seems to place an absurd, anthropocentric weight on the history of the cosmos. Furthermore, experiments with increasingly complex non-conscious systems, from photodetectors to today's AI algorithms, can perfectly record quantum events without any human in the loop, suggesting observation is a physical process, not a magical mental one. Yet, despite these powerful objections, the idea persists, fueled by deep philosophical questions. It blurs the line between the physical and the mental, suggesting that mind is not a passive passenger in the universe, but an active participant in its very manifestation. It resonates with certain interpretations of meditation and mysticism, where focused attention is said to shape reality. In this view, entanglement becomes more than a physical phenomenon. It is a cosmic mirror reflecting the profound connection between inner experience and outer world, hinting that the separation between observer and observed might be the most fundamental illusion of all. While it remains on the fringes of testable science, the conscious observer theory forces us to confront the uncomfortable silence at the heart of quantum theory. What, in the end, brings the potential into the actual, and in a universe veiled in probabilities, is the simple act of looking the very thing that summons the world into being. The transactional interpretation's handshake across time forces us to confront a radical possibility. Our deep-seated belief that the past causes the future might be a stubborn illusion, a comforting story we tell ourselves in a universe where time's arrow is far more flexible. This is the world of time-symmetric quantum mechanics, where influences can flow backward as easily as forward, and entanglement becomes a fixed agreement negotiated between past and future. To see this in action, we must turn to one of the most mind-bending experiments ever conceived, the quantum eraser. Imagine a simple setup where a single photon is fired at a screen through a barrier with two slits. As you know, the photon behaves like a wave, passing through both slits at once and creating an interference pattern of light and dark bands on the screen. This pattern is the signature of quantum weirdness, proving the photon took all possible paths. Now, place a detector at one slit to see which path the photon actually takes. The moment you do this, the interference pattern vanishes. By gaining which path information, you force the photon to behave like a particle, collapsing its wave function. The story seems straightforward. Your measurement in the present determines the photon's past behavior, but the quantum eraser adds a stunning twist. What if, after the photon has already hit the screen and been recorded, you then destroy the which path information? You erase the knowledge of which slit it took. Astonishingly, when scientists do this, the interference pattern magically reappears in the data, even though the measurement happened long after the photon's journey was complete. It is as if your choice in the future retroactively changed whether the photon acted as a wave or a particle in the past. The photon's history was not fixed until after you decided what to do with the information. In the time-symmetric view, this is not a paradox, it is the mechanism of reality. The transaction was not finalized until the future possibility of erasure was incorporated into the negotiation. The photon's origin sent out offer waves for both particle-like and wave-like futures. Your initial detector setup accepted the particle-like offer, completing that transaction. But your later eraser device sent a new, backward-in-time offer wave, reopening the negotiation and allowing the wave-like transaction to be completed instead. The past at the quantum level remains malleable until all future interactions are settled. For our entangled particles, this means their perfect correlation is not established at the moment of creation or measurement alone. It is the result of a time-symmetric deal that considers the entire history of the system, from birth to every possible future interaction. The spins were always going to match, not because of a signal, but because the final, agreed-upon transaction between their point of origin and all their potential detection events demanded it. This turns causality on its head. We see a sequence. Particle A is measured, then particle B is found to match. We assume A's measurement caused B's state. But in this framework, the measurement of A and the matching result of B are both effects of a single, timeless cause. The complete transaction, which includes the fact that both measurements would eventually be made and compared, is the true cause. It is like watching a movie for the second time. The hero's decision at the end seems to cause the opening scene, but in truth, the entire story was written as one piece. Our linear experience of time is just us watching the film play out frame by frame. The quantum world, it seems, has the entire script from the very beginning, and entanglement is one of its most carefully plotted narrative devices, ensuring every part of the story remains perfectly consistent, no matter which direction you read it from. A script written across time suggests a universe where the future can whisper to the past, but what gives that whisper a direction? Why do we remember yesterday but not tomorrow? The answer might not be found in the ticking of a clock, but in the silent growth of connections in the dark. This is the thermal time hypothesis, a theory that boldly links the mysterious flow of time to the fundamental laws of heat and the spread of quantum entanglement. It proposes that time is not a fundamental river flowing through the cosmos. It is a side effect, a story told by systems as they stumble toward equilibrium. In our everyday world, we see this clearly. A cup of hot coffee left on a table does not suddenly get hotter. It cools down, its heat spreading out into the room until everything reaches the same lukewarm temperature. This irreversible process from order to disorder defines the arrow of time for us. The hot coffee is a state of low entropy, a concentrated order. The cooled coffee is high entropy, a dispersed chaos. We always move from low to high, and that direction is what we experience as the future. Now, step into the quantum realm. The thermal time hypothesis suggests that what we call entropy, that measure of disorder, is deeply connected to quantum entanglement. When two particles become entangled, they share information, creating a correlation. This correlation is a form of order, a specific kind of structure in the quantum state. As a complex quantum system evolves, its particles become more and more entangled with each other and with their environment. The web of quantum correlations grows denser and more complex. This increase in entanglement, according to the theory, is the increase in entropy, and that increase is what we perceive as the forward march of time. Imagine the universe just after the Big Bang in a state of incredibly low entropy. It was hot, dense, and remarkably simple. There was very little structure and, crucially, very little complex entanglement. As it expanded and cooled, particles began to interact and the first quantum correlations were forged. The web began to spin. With each interaction, entanglement spread. The quantum information became more scrambled and distributed, and the entropy of the cosmos increased. The direction of this process from a simple, low entanglement state to a complex, highly entangled one gave birth to the arrow of time itself. In this view, a clock does not measure some external time. It is a physical system whose own increasing entanglement with the environment provides a regular tick, a heartbeat of the growing quantum web. This leads to a breathtaking and slightly eerie conclusion. Where there is no entanglement, there may be no clear flow of time. In a region of perfect quantum isolation, where a system does not interact or correlate with anything else, entropy would not increase. The distinction between past and future would blur into meaninglessness. Time would not pass, it would simply be. This might explain why time seems to slow near a black hole's immense gravity, where space-time is warped and quantum connections are stretched to their limit. It suggests that the ultimate heat death of the universe, when everything reaches maximum entropy and perfect thermal equilibrium, might also be the end of time as a flowing phenomenon. There would be no more net increase in entanglement, no more processes to give direction to existence, just a vast, silent, and timeless sea of uniform correlation. So the next time you feel a moment slip into the past, consider that you are not just moving through time. You are participating in the universe's grand, irreversible project of weaving itself into an ever more entangled, interconnected whole. The flow you feel is the cosmos knitting itself together, one quantum connection at a time. The silent growth of entanglement might feel like a cosmic process, but perhaps it is something far more mechanical. There exists a theory that strips the universe of all mystery and paints it as a vast ticking machine. This is the cellular automaton universe, an idea that suggests reality is nothing more than an immense, deterministic computer program. In this view, the cosmos is a grid of unimaginable scale, with each cell representing a tiny piece of space-time. Each cell can be in one of a finite number of states, like a pixel being either on or off. And the entire universe evolves through time according to a fixed set of simple, local rules. These rules dictate how each cell's state changes based on the states of its immediate neighbors. From this starkly simple foundation, everything we see, galaxies, consciousness, and even the spooky dance of quantum entanglement, is supposed to emerge. The most famous example of such a system is Conway's game of life. On a two-dimensional grid, squares are either alive or dead. 4 basic rules determine, based on a square's 8 neighbors, whether it lives, dies, or is born in the next step. Run these rules, and from random starting patterns, astonishingly complex structures emerge. Gliders sail across the grid, stable pulsars blink rhythmically, and even self-replicating patterns can arise. All this rich, dynamic behavior comes from mindlessly applying a handful of trivial instructions. Proponents of the cellular automaton universe ask us to scale this idea up to reality itself. What if the fundamental laws of physics are not elegant equations describing fields and forces, but are actually the update rules for a cosmic grid? In such a universe, there is no true randomness, only the appearance of it from our limited perspective within the computation. Every event, from the decay of an atom to the firing of a neuron, is predetermined by the initial state of the grid and the relentless step-by-step application of the rules. So where does quantum entanglement fit into this clockwork picture? If the rules are strictly local, only affecting a cell's immediate neighbors, how can 2 particles instantly correlate across light years of empty grid cells? The answer lies in the concept of emergent complexity. In a cellular automaton, local rules can give rise to global patterns that are effectively non-local. Think of a glider in the game of life. It is not a single cell. It is a specific pattern of 5 cells that moves diagonally across the grid. To an entity living within that grid, the glider is a single, coherent object. If such an entity could perform experiments, it might find that 2 distant gliders are mysteriously linked, their movements perfectly synchronized. From outside the grid, we see the truth. The gliders are not separate objects sending signals. They are both manifestations of the same underlying pattern in the cellular data, a pattern generated by local rules but expressing a correlation that spans the grid. In our hypothetical cosmic automaton, quantum entanglement could be a similar illusion. Two particles that seem separate and mysteriously connected might be two facets of a single, complex, non-local pattern in the deeper computational substrate. Their correlation is written into the data from the beginning, a fixed feature of the cosmic code playing out. When we measure one, we are not causing a collapse or sending a signal. We are merely reading a part of the pattern, and the rules of the automaton ensure the other part of the pattern matches perfectly, no matter the apparent distance. This theory seeks to explain all quantum weirdness as an emergent property of a deeper, classical, and utterly deterministic computation. It promises a universe without fundamental uncertainty, where even the spookiest action is just a glitch in our perception, a failure to see the sprawling, predetermined tapestry of the grid. It offers a cold comfort. The mystery of connection is solved, but at the cost of reducing all of existence, including our thoughts and choices, to the output of a silent, celestial machine, ticking away in the dark since the first step of the program. A cosmic computer reduces the universe to a predetermined grid, but what if we have been asking the wrong kind of question all along? We have spent decades trying to predict what particles will do, charting probabilities and wave functions. But a radical new framework suggests we should stop asking what will happen and start asking what can be done. This is constructor theory, and it reframes all of physics not as a story of cause and effect, but as a catalogue of possible and impossible tasks. In this view, the universe is not defined by particles and forces, but by transformations. Which transformations are possible, which are impossible, and what physical resources are required to achieve them. The fundamental laws become statements about these possibilities. For example, the law of conservation of energy is recast as the statement, building a perpetual motion machine is impossible. The theory of relativity says sending a signal faster than light is impossible. This shifts the entire goal of physics from predicting outcomes to understanding the limits of what can be constructed. And right at the heart of this new catalog, enabling transformations that should be utterly impossible, is quantum entanglement. In the classical world, certain tasks are simply forbidden. You cannot perfectly copy an unknown quantum state, a rule called the no-cloning theorem. You cannot measure a particle without disturbing it, and you certainly cannot teleport an object from one location to another without moving it through the space in between. Yet, with the resource of entanglement, every single one of these impossible tasks becomes possible. Let us take quantum teleportation, the most dramatic example. The goal is not to magically zap a physical object, but to transfer the exact, fragile quantum state of a particle from one place to another, destroying the original in the process. Classically, this is hopeless. You cannot scan the particle to read its state because measurement destroys quantum information. But with entanglement as a resource, it becomes a precise laboratory routine. Here is how it works. First, you create a pair of entangled particles and send one, call it particle B, to your friend across the galaxy. You keep the other, particle A. Now you have the particle you want to teleport, particle X. You perform a special kind of joint measurement on particle X and your half of the entangled pair, particle A. This measurement entangles them, but in doing so, it completely scrambles the state of particle X and your particle A. It seems like you have destroyed the very information you wanted to send. But here is the magic of the constructor perspective. That measurement also instantly affects the entangled partner, particle B, now far across the galaxy. It does not send the information itself. It places particle B into a state that is almost but not quite a perfect copy of the original particle X. It is like particle B has been transformed into a locked version of X. The key to unlock it is the specific result of your measurement, which is just two classical bits of information, a simple 1 or 0. You send that ordinary, light speed limited message to your friend. When they receive it, they apply the corresponding correction to their particle B, and instantly particle B becomes an exact replica of the original particle X's quantum state. The original particle X is gone, its information transferred. From the constructor theory viewpoint, the task of teleporting quantum information is impossible without the specific resource of an entangled pair. The entangled pair is not a signal, it is a construction tool, a universal adapter that makes an otherwise forbidden transformation achievable. Entanglement, in this light, is not just a strange correlation to be explained. It is a currency, a raw material for building new realities. It is the oil that lubricates the most powerful quantum machines. This theory elevates information to a primary physical substance as real as matter or energy. And it sees entanglement as the crucial constructor that allows information to be manipulated in ways that defy every classical intuition. The universe, according to this perspective, is a workshop. The laws of physics are its blueprint of allowable projects, and quantum entanglement is the master key, unlocking doors to realms of possibility we once believed were sealed shut forever. The master key of entanglement unlocks a workshop where reality itself can be rewired. But what if the most reliable locks are not built from matter but from shape? There exists a class of quantum systems where the deepest truths are not found in the positions of particles or the strength of fields, but in the timeless, global shape of the stage itself. This is the realm of topological quantum field theories, where entanglement becomes as durable as a knot in spacetime. In our familiar three-dimensional world, particles come in two basic types. Fermions, like electrons, obey one set of statistical rules, while bosons, like photons, obey another. But in a flat, two-dimensional world, an entirely new kind of particle becomes possible. These are called anyons, and their behavior defies the old categories. The magic of anyons lies not in what they are, but in what happens when you move them around each other. In our world, if you take two identical electrons and swap their positions, the quantum wave function describing them picks up a simple minus sign. Swap them again, and you are back to where you started. It is like turning a book face down, then right side up. With anyons in a two-dimensional plane, the rules are far richer. Swapping two anyons does not just give a minus sign. It can rotate their shared quantum state by any fractional phase, hence the name enyon. And here is the crucial part. If you perform a sequence of swaps, braiding the world lines of these particles around each other in time, the final quantum state depends only on the topological pattern of the braid. It does not care about the precise speed of the movement, the exact distance, or any minor jiggles along the way. Just as a knot in a shoelace remains a trefoil knot whether the lace is thick or thin, the quantum information encoded in a braid of anyons is protected by its topology. This robustness is the holy grail for quantum computing. Ordinary quantum bits are infamously fragile, decohering at the slightest environmental whisper. But a quantum bit built from the braiding of anyons, a topological qubit, would be different. Its information is stored not in a vulnerable particle state, but in the global braid pattern itself. You could poke and prod the individual particles, and as long as you do not complete a full braid that changes the topology, the encoded information remains perfectly safe. It is like writing a message not on paper but in the winding path of a river across a landscape. You could litter the banks with debris, but the course of the river, its topological history, remains untouched. Where does entanglement fit into this topological fortress? In these systems, entanglement is not a fleeting correlation. It is the very substance from which the anyons are made. In materials like fractional quantum Hall systems, anyons emerge as collective excitations, quasi-particles that arise from the profoundly entangled dance of billions of electrons constrained to a two-dimensional plane. The exotic braiding statistics are a direct manifestation of this global, topological entanglement. The particles themselves are knots in the quantum fabric. This leads to a staggering possibility for our understanding of everything. If the most stable quantum information resides in topological features, could spacetime itself be described by a topological quantum field theory? In such a framework, the geometry of the universe, the distances and curvatures we measure, would be secondary, emergent properties. The fundamental description would be topological, dealing only with the invariant, braid-like connections that define the quantum vacuum. The smooth, continuous spacetime of general relativity would arise from a vast, entangled network whose stable features are topological, immune to local noise and fluctuation. In this vision, the universe is not a collection of things in a container. It is a dynamic, evolving knot of correlations where what persists, what is real, is only that which cannot be undone by a gentle deformation. Entanglement becomes the thread, and topology is the pattern that gives it lasting form, suggesting that the ultimate laws of nature may be written not in the language of forces, but in the silent, immutable grammar of shape and connection. The silent grammar of shape hints at a universe built on information, a possibility that leads us to a theory that has leapt from fringe philosophy to serious debate. Could the discrete, rule-bound nature of quantum mechanics be a clue that we are living inside an artificial construct? The simulated universe hypothesis proposes that our entire cosmos, with all its galaxies, history, and laws, is not base reality, but a sophisticated simulation running on a computer of unimaginable power in a higher-order universe. From this startling vantage point, the bizarre phenomenon of quantum entanglement takes on a new, almost mundane character. It may not be magic, but a sign of efficient programming. In a vast simulation, every star, every atom, and every conscious thought would need to be rendered and calculated. Tracking trillions upon trillions of independent particles interacting across light years in real time would be a computational nightmare demanding infinite processing power. But what if, to optimize performance, the simulation's underlying code links certain variables together? This is where entanglement fits in. The spooky, instantaneous correlation between two particles could be a clever shortcut. Instead of calculating the state of each particle independently at every moment, a massively redundant task, the simulation's engine can treat an entangled pair as a single, unified object. When you measure one, the program simply updates both entries in its cosmic database at once, enforcing the correlation with no need for a physical signal to travel the intervening space. Non-locality, then, is not a violation of cosmic rules, but a feature of optimized code. It is a data compression technique, a way for the simulation to save precious processing cycles by not rendering the empty space between entangled entities as truly independent. The discrete, quantized nature of reality we see in quantum mechanics, the fact that energy, spin, and other properties come in specific, indivisible chunks, fits perfectly with this idea. Computers operate digitally on bits of information. A simulated universe would naturally have a pixelated, digital foundation at its smallest scale, which is exactly what our physics suggests. The famous double-slit experiment, where particles behave as waves until observed, could be interpreted as a rendering trick. The simulation only calculates a definite path for a particle, collapsing the probability wave when that information is needed by an observer within the simulation, conserving resources until the last possible moment. This theory, while utterly speculative and currently untestable in any conventional way, forces a profound shift in perspective. It asks us to view the deepest mysteries of physics not as fundamental truths of nature, but as artifacts of a computational architecture. The universe's speed limit, the Planck length, the very fact that information seems to be the irreducible substance of everything, all could be seen as the parameters and data types of the simulation. If this is true, then entanglement is not a thread connecting distant parts of reality. It is a pointer in a cosmic array, a line of code that tells the program these two variables are linked, update them together. The eerie silence of quantum connection is not a mystery of physics, but the quiet hum of a perfectly efficient machine, running the code of our existence in the background of a reality we can never see. A simulated universe runs on code, but what if the code is not a program, but a network of pure geometry? To find the source, we must leave behind the metaphor of software and enter a world where space itself is woven from discrete, vibrating threads. This is the domain of loop quantum gravity, a leading contender for a true theory of quantum gravity, and it paints a picture of entanglement so fundamental it is stitched into the very pixels of reality. While string theory imagines tiny, vibrating strings in a pre-existing space, loop quantum gravity takes a more radical step. It asks what happens if we apply the principles of quantum mechanics not to particles within space, but to the fabric of spacetime itself. The answer is that space is not smooth and continuous. It is granular, composed of indivisible, finite quanta. Imagine the fabric of your shirt. Up close, it appears smooth, but under a powerful microscope, you see it is woven from individual threads. Loop quantum gravity suggests spacetime is like that shirt. Its threads are called spin networks. A spin network is not a thing in space, it is space. Picture a vast, ever-changing web of lines or links connecting nodes. Each link carries a label, a quantum number representing a tiny, fundamental unit of area. Each node represents a fundamental unit of volume. The entire three-dimensional geometry of the universe at a given instant is described by the pattern of this web, which nodes are connected and with what values. This network does not live in space, its connections define space. Proximity is not about distance in some container, but about direct linkage in the graph. Now, how does this quantum space evolve? The spin network does not sit still. In the leap from one instant to the next, the graph changes. Links reconnect, nodes merge or split. These dynamical processes are described by spin foams, which are like the four-dimensional histories of these three-dimensional spin networks. They are the quantum spacetime equivalent of a movie made from individual frames. So where does our mysterious quantum entanglement reside in this geometric tapestry? The connection is profound. In loop quantum gravity, the quantum state of geometry is a superposition of many possible spin networks. Entanglement between different parts of space is not something that happens within the network. It is a property of the network's very structure. When two regions of space are entangled, it means their geometric descriptions. The specific configurations of spins and links are quantum correlated. More strikingly, the links of the spin network themselves may be the physical carriers of entanglement. A single link connecting two nodes does not just tell us about area, it could encode the entanglement entropy between the two volumes it joins. This leads to a breathtaking possibility hinted at by the holographic principle. The famous formula that says the entropy of a black hole is proportional to its horizon's area might find its direct microscopic explanation here. Each fundamental Planck scale patch of area on a black hole's surface could correspond to a single link in the underlying spin network piercing that surface. The entanglement between the inside and outside of the black hole could be literally counted by the number of these intersecting links. In this view, when you entangle two particles, you are not creating a new link in a pre-existing space. You are exciting or rearranging the fundamental geometric threads that were already there, the very threads that constitute the void between them. The spooky action at a distance becomes a change in the quantum state of the spin network that defines the intervening space itself. The particles are not communicating across a gap, they are two localized excitations of a single, interconnected geometric entity. This theory offers a radical resolution. It suggests that the weird non-locality of quantum mechanics and the smooth locality of general relativity are not at war. They are two sides of the same coin, both emerging from a deeper, discrete geometry where connection is primary and separation is the illusion. The universe, according to loop quantum gravity, is a cosmic knot, a dynamic weave of quantum relationships, and every entangled pair we create is a tiny echo of the grand geometric pattern from which all of space and time is born. A universe woven from geometric threads finds its most famous melody in a symphony of higher dimensions. String theory offers a radically different vision for unifying the quantum and gravitational worlds, and within its elegant mathematics, entanglement finds a home not in points but in vibrations. At its heart, string theory proposes that the fundamental constituents of reality are not zero-dimensional particles, but incredibly tiny, one-dimensional loops or strands of energy vibrating at specific frequencies. The different vibrational modes of a single string give rise to every particle we see, from the humble electron to the mighty photon. In this framework, what we perceive as a particle's properties, like its mass and charge, are simply notes played on a cosmic string. This shift from point to string has profound implications for entanglement. When two point-like particles become entangled, their connection seems ghostly and abstract. But when the objects are strings extended through a tiny slice of space, the concept of connection gains a new texture. Two strings can become intertwined, their one-dimensional shapes wrapping around each other or sharing a common vibrational pattern. Their entanglement is no longer a correlation between two abstract numbers, but a physical braiding of the fundamental fabric of reality itself. Furthermore, string theory introduces the idea of brains, short for membranes. These are higher dimensional objects where strings can end or move within. Our entire three-dimensional universe could be a vast three-brain floating in a higher dimensional bulk space. Strings attached to such a brain represent the particles of our world. Entanglement can then occur not just between strings, but between different regions of a brain, or even between separate brains, creating correlations across dimensions we cannot directly perceive. To make sense of this multidimensional landscape, string theorists rely on powerful symmetries called dualities. These are mathematical transformations that reveal two seemingly different descriptions of physics to be exactly equivalent. One of the most illuminating for entanglement is T-duality. It shows that a string moving in a space that is curled up into a tiny circle of a certain radius is physically identical to a string moving in a space with a circle of the inverse radius. A large wrapped dimension and a small unwound dimension are two faces of the same coin. This has a stunning consequence for locality, the idea that objects are only influenced by their immediate surroundings. In one description, a process might look perfectly local, confined to a small region. But after applying a T-duality transformation, the same process can appear wildly non-local, with influences jumping across vast distances in the dual geometry. This provides a revolutionary mathematical tool. It suggests that what we experience as spooky, non-local entanglement in our familiar description of physics might be perfectly local and understandable from a different, dual perspective. The weirdness is not in the phenomenon, but in our chosen coordinates, our limited view of the cosmic stage. String theory thus reframes the mystery of quantum connection as a hint of a deeper, unified geometry. The instantaneous link between two particles could be the shadow of a string that is physically stretched between them in a higher dimension, or the result of a duality that blends here and there into a single, coherent whole. In this vision, gravity and quantum mechanics are not at war. They are different movements in the same string symphony, and entanglement is the harmony that binds every note together, resonating through the hidden curls of space itself. The symphony of strings leads to a profound silence, a question that has haunted physics for a century. Why does gravity, the force that sculpts galaxies, refuse to fit into the quantum framework that governs everything else? Perhaps the answer is that gravity is not a force at all. This is the radical proposal of emergent gravity, a theory pioneered by physicist Eric Verland, which suggests that gravity is not fundamental but an entropic effect, a side effect of the universe's relentless drive toward disorder. powered by quantum entanglement. To grasp this, we must revisit the concept of entropy, often described as a measure of chaos or randomness. But a more precise definition is that entropy is a measure of hidden information, the number of microscopic arrangements that could produce the same macroscopic appearance. A melted ice cube has higher entropy than a frozen one because there are vastly more ways for its water molecules to be arranged in a puddle than in a rigid lattice. Now, Verland asks us to take the holographic principle seriously. If our three-dimensional world is a projection from a two-dimensional boundary where information is stored, then what we perceive as empty space is actually a vast holographic screen teeming with quantum information. Every bit of that information is entangled. The entanglement entropy of this screen is a measure of the information hidden in these microscopic quantum correlations. Here is the breathtaking leap. Verland proposes that when a massive object like a planet is placed near this holographic screen, it displaces information. Think of it like a heavy ball resting on a stretched membrane. The ball pushes down, distorting the membrane. In the holographic picture, the mass of the object changes the entanglement entropy of the quantum bits on the screen in its vicinity. Nature, according to the second law of thermodynamics, always tends toward increasing entropy. So when the entropy distribution is altered by the presence of mass, the system responds to restore equilibrium. That restorative tendency, the natural drift toward higher entropy, is what we experience as the force of gravity. The planet does not pull on you with a mysterious force. Instead, your movement toward it increases the total entanglement entropy of the system. You are not falling, you are being swept along by the natural gradient of information, like a leaf caught in a stream flowing toward a region of greater disorder. This elegantly explains inertia as well. An object at rest tends to stay at rest because moving it would require changing the entanglement pattern of a vast number of quantum bits on the holographic screens surrounding it. Resistance to acceleration is not an intrinsic property of matter, but the informational cost of reorganizing the fabric of reality. The force we feel when we push something is its entanglement structure pushing back. In this framework, dark matter, that mysterious substance inferred from galaxy rotations, might not be a particle at all. It could be an entropic effect, an extra gravitational pull arising from the way the universe's quantum information is distributed on the largest scales beyond the visible stars. This idea ties the cosmic force of gravity directly to the quantum phenomenon of entanglement. The fabric of spacetime is not warped by mass as Einstein taught us. Instead, mass modifies the entanglement entropy of the underlying quantum information, and the resulting gradient in information density manifests as the curvature we call gravity. It suggests that the force that holds our feet to the ground is at its core a statistical urge, a collective memory effect written in the quantum connections of the universe. Gravity is not a master of the cosmos, but a servant to entropy, and entanglement is the language in which its orders are written. Gravity's entropic pull emerges from a sea of quantum data, but who decides how that data is organized? Every measurement we make, every fact we record, depends on a silent, unexamined foundation, the reference frame. In Einstein's relativity, motion and simultaneity are relative to an observer's inertial frame. But what if that principle runs deeper into the quantum heart of reality itself? This is quantum reference frame theory, and it proposes that not just motion, but the very definition of a physical system, what is entangled with what depends on the quantum state of the observer who is measuring it. Imagine you are floating in a featureless void with two particles, A and B. In your reference frame, you carefully measure them and find they are perfectly entangled, their fates mysteriously linked. Now, a second observer arrives, but with a crucial difference. Their own quantum state, their very physical constitution, is entangled with one of your particles from the start, perhaps because of some past interaction they had with it. When this new observer now looks at the same scene, their description of reality can be radically different. From their quantum perspective, it might appear that particle A is now entangled with them, and particle B is just an ordinary, independent particle. The entanglement you saw between A and B has, from their viewpoint, vanished or transferred. This is not an error or an illusion. It is a fundamental relativity of quantum information. Just as two observers moving at different speeds disagree on the order of events, two observers in different quantum states can disagree on which parts of the universe are entangled. There is no privileged, God's eye view that declares one description absolutely true. All descriptions are equally valid relative to the quantum reference frame of the observer making the measurement. The theory provides a precise mathematical machinery to translate between these frames, much like Lorentz transformations translate between inertial frames in special relativity. To make this concrete, think of a cosmic game of musical chairs played with quantum connections. You, the observer, are also a chair. The particles are players. In your frame, you see players A and B holding hands, entangled. But if you suddenly become entangled with player A from your new perspective, you are now the one holding his hand. Player B is left without a partner in your story, appearing free. Another observer entangled with B would tell the opposite story. The web of connections isn't fixed. It is a dynamic pattern that shifts depending on where you, the observer, are woven into the fabric. This framework elegantly generalizes Einstein's principle of relativity to its ultimate conclusion. In classical relativity, all inertial frames are equal for the laws of physics. In quantum reference frame theory, all quantum frames are equal for the description of information and entanglement. It dissolves the paradox of spooky action by showing that the action is only spooky from a frame that treats the two particles as separate, isolated systems. From a frame that includes the entire entangled network particles, measuring devices, and observers as one quantum whole, there is no action at a distance, only a unified state evolving together. The non-locality is in the eye of the beholder, a consequence of trying to carve a seamless quantum whole into separate classical pieces. It suggests a profound humility in our quest to understand the universe. We cannot stand outside the quantum system to describe it objectively because we are always part of it, our own atoms and instruments entangled with the phenomena we study. The act of observation is not a passive reading of a pre-written script, but an active participation that selects from a multitude of equally real perspectives the story our particular quantum frame allows us to see. The threads of entanglement are not absolute lines on a cosmic map, but relational pathways whose very existence depends on the point from which the map is drawn. This relativity of perspective suggests a universe of shifting truths, but what if even quantum mechanics itself is not the final word? Beyond the strange world of superpositions and entanglement lies a frontier of possibility, a realm of theories that dare to imagine a physics stronger, deeper, and even weirder than quantum theory. These are the post-quantum theories, speculative frameworks that seek not just to interpret quantum mechanics, but to transcend it, often in the quest to finally marry it with gravity. At the heart of this ambition lies a simple, profound question. Is the spooky connection of quantum entanglement as strong as a connection can possibly be, or could there be something even spookier? Quantum mechanics sets a very specific limit on how correlated two particles can be. This limit is known as the Thylson bound, named for the mathematician who proved it. It is a cosmic speed limit for correlation, built into the very mathematics of the theory. In any quantum experiment, no matter how cleverly you arrange your measurements, the strength of the non-local link between entangled particles will never exceed this bound. It is as if nature has placed a governor on the engine of weirdness. But why? Post-quantum theories ask what would happen if we removed that governor. They explore the possibility of super-quantum correlations, hypothetical connections that would violate the Thylson bound, creating correlations stronger than anything quantum mechanics allows. In such a world, the results of measurements on entangled particles would be even more tightly synchronized, predicting each other with a certainty that makes quantum entanglement look almost classical by comparison. Imagine our two coins spinning in their boxes. In a quantum world, their correlation is strong, but it still obeys statistical rules that leave a tiny window for mismatch governed by probability. In a super quantum world, opening one box would not just tell you with high probability what is in the other. It would tell you with absolute 100% certainty every single time for any conceivable measurement you could choose. The link would be so powerful it would erase any semblance of independence. What could possibly motivate such a radical idea? The drive often comes from the stubborn puzzle of quantum gravity. Our two most successful theories, quantum mechanics and general relativity, are magnificently accurate in their own domains, but they clash catastrophically when forced together. Some physicists suspect that to unify them, we may need to reformulate one or both from the ground up. If spacetime itself is emergent from a more fundamental structure, as many theories suggest, then the rules of quantum information that apply within that spacetime might also be emergent, approximate rules. The true, fundamental theory beneath might operate with different, perhaps stronger, principles of connection. In this deeper layer, what we call entanglement might be a pale shadow of a more profound geometric linking. Exploring these super-quantum theories is not just mathematical fantasy, it is a stress test for our understanding of reality. By probing the very limits of what is possible, the Thylacine bound, we learn what is essential about our universe. Why does this bound exist? Is it a fundamental law of information, or is it a contingent feature of our particular cosmic epoch? A rule that could break down under conditions of extreme gravity, like inside a black hole or at the Big Bang. Some proposals suggest that to make sense of a holographic universe where gravity and quantum information are two sides of the same coin, we might need a broader information theory where the old quantum limits no longer apply. This would imply a complete reformulation of information theory itself. Our current digital world is built on classical bits and quantum bits. A post-quantum reality might be built on something else entirely, a new kind of informational currency that allows for correlations so strong they redefine what it means for two things to be separate. The implications are dizzying. Communication, computation, and our very conception of causality could be upended. Yet, for all their speculative power, these theories face a formidable barrier. No experiment has ever shown a violation of the Thylacine bound. Quantum mechanics, with all its spookiness, has passed every test with flying colors. This suggests that if a deeper theory exists, it must perfectly mimic quantum mechanics in all the regimes we have so far been able to explore, only revealing its super-quantum heart in realms we cannot yet access. So we are left at a fascinating precipice. We have a theory, quantum mechanics, that works flawlessly but feels incomplete. And we have dreams of a deeper theory that might complete the picture, dreams that currently live in the mathematics of possibility. The search for post-quantum physics is ultimately a search for the next revolution, a whisper from the future of physics suggesting that the quantum world, for all its mystery, might just be the first layer of a far stranger and more connected reality waiting to be discovered. The dream of a deeper theory takes us back to the very beginning of everything, to a moment when the entire cosmos was smaller than a single atom. At that scale, quantum rules reigned supreme. This leads to a staggering possibility that the infant universe was not just a hot, dense soup of particles, but a single, profoundly entangled quantum state. Every point, every potential particle was linked to every other in a unified whole. Then, in a fraction of a second, cosmic inflation struck, a period of unimaginably rapid expansion that stretched this microscopic quantum seed into the macroscopic universe we see today. But what happens to quantum entanglement when the fabric of space itself inflates faster than light? The correlations do not vanish. They are stretched, imprinted onto the geometry of the newborn cosmos. Think of a tiny, intricate pattern drawn on the surface of a balloon. Now, blow up that balloon to the size of a city. The pattern is still there, vastly enlarged, its fine details smooth but its overall structure preserved. Inflation is thought to have done exactly this to the primordial quantum fluctuations, the tiny ripples in the universal quantum field. Those ripples were born entangled, their properties correlated across minute distances. As space ballooned, those minute distances were stretched to spans of millions of light years. The quantum correlations of the microscopic beginning were blown up to become the seeds of cosmic structure. This means the pattern of galaxies we see in the sky today, the vast filaments and voids of the cosmic web, might trace its origin back to a network of quantum entanglement in the first instant of time. The cosmic microwave background, the afterglow of the Big Bang, is our most detailed baby picture of the universe. Its subtle temperature variations, the hot and cold spots, are the direct descendants of those inflated quantum ripples. If those ripples were truly entangled, that signature might be hidden within the pattern. Scientists are searching for specific, non-random statistical signatures in the cosmic microwave background that could only arise from primordial quantum entanglement, a fossilized whisper of the universe's original unity. Finding such a signal would be revolutionary. It would mean that the largest structures in the cosmos are held together at their most fundamental level by the same quantum glue that links particles in a lab. The emptiness between galaxies would not be truly empty, but threaded with the ghostly, stretched-out correlations of a quantum past. It suggests a profound symmetry. The same phenomenon that seems so spooky and small in our experiments may be the very mechanism that wrote the blueprint for stars, planets, and us. We would be living in a universe that is, at its core, non-local on the grandest possible scale, a cosmic testament to the idea that everything was once, and perhaps still is, connected in a way that defies our ordinary understanding of space and separation. The cosmic web woven from primordial entanglement forces us to confront an even deeper mystery. What if the threads of connection are not just physical but also conscious? This is the territory of panpsychism, a theory that ventures beyond physics into philosophy, proposing that consciousness or experience is not a rare product of complex brains, but a fundamental property of all matter. In this view, the universe is not a dead machine, but a living, experiencing entity. Every electron, every photon, every quark possesses some minute, intrinsic form of experience, a glimmer of what we might call mind. It is a spectrum with the simple, raw feeling of a particle at one end and the rich, self-reflective awareness of a human being at the other. From this perspective, the hard problem of consciousness, the question of how subjective experience arises from objective matter, is turned on its head. Experience does not arise. It was there from the start, as fundamental as mass or charge. So where does quantum entanglement fit into a conscious cosmos? If every particle carries a tiny spark of inner life, then entanglement could be more than a mathematical correlation or a geometric link. It could represent a form of primitive connection or even communication between these most basic constituents of reality. When two particles become entangled, their individual, minute experiences might become synchronized or unified in a way that transcends space. Their spooky action at a distance would not be a transfer of information, but a sharing of state, a merging of their inner perspectives into a single, correlated experience. Think of it not as a signal, but as a harmony. Imagine two tuning forks, each humming with its own faint, intrinsic vibration. When they are entangled, it is as if they are placed on the same resonant wooden base. Strike one and both begin to hum in perfect sympathy. The base is the quantum connection, but the hum is the experience. The forks do not send a message to each other. They simply, instantly, share a common state of vibration because they are part of a unified system. In the panpsychist view, the particles are like those forks, and their intrinsic experience is the hum. Entanglement is the resonance that binds their hums together. This idea seeks to marry two great mysteries into one. The mystery of quantum non-locality and the mystery of consciousness might both be facets of a deeper truth that the universe is fundamentally experiential and interconnected. It suggests that the weirdness of the quantum realm is not a bug, but a feature of a reality where inner life is woven into the fabric of everything. Of course, this theory is met with deep skepticism in scientific circles. How could we ever test if an electron has an inner life? What would that even mean? Critics argue it explains nothing, merely labeling the unknown with another unknown. Yet, its proponents see it as the most elegant way to avoid the magical emergence of consciousness from utterly insentient matter. It offers a vision of a cosmos that is continuous, where mind is not a sudden, miraculous accident in a tiny corner of a vast, dead universe, but an inherent quality of the whole. In such a universe, our own profound sense of connection to the world around us, our intuition that we are part of something greater, might find a strange echo in the quantum bonds linking every particle. The entanglement we measure in labs could be the physical signature of a silent, universal symphony of experience, a whisper of consciousness at the very root of reality itself. The silent hum of a conscious cosmos finds a startlingly precise translation in the language of ones and zeros. This brings us to a theory that frames the entire universe not as a symphony of experience, but as the output of a cosmic calculation. It is called digital physics, or more poetically, the it from bit doctrine, championed by the visionary physicist John Archibald Wheeler. His proposal was as radical as it was simple. What if every particle, every force, every event in the physical world, the it of reality, ultimately derives from immaterial bits of information? In this view, the bedrock of existence is not energy or matter, but the binary yes or no answers to an endless series of quantum questions. Is the spin up or down? Is the photon here or there? At the most fundamental level, the universe is not made of stuff but of choices. If the cosmos is a vast informational process, then quantum entanglement becomes elegantly clear. It is not a mysterious force linking distant objects. It is a perfect correlation between the most basic bits of data in the cosmic program. Imagine the universe as an unimaginably vast and intricate quantum computer. The space around you, the stars above, are not its hardware, but the stunningly complex visual display generated by its computations. The hardware is the network of quantum bits or qubits humming with potential. Entanglement, then, is the essential wiring of this computer. It is the logical connection that allows separate qubits to share information and perform operations in unison, enabling the complex calculations that give rise to our seemingly continuous three-dimensional world. To see how this works, think of a simple pixel on your screen. That pixel can be any color, but at the deepest level of the machine, it is controlled by binary code, a specific pattern of electrical bits being on or off. In Wheeler's cosmic vision, a particle like an electron is analogous to that pixel. Its properties, position, momentum, spin, are the color we perceive. But those properties are not primary. They are the readout, the it, generated by a deeper layer of informational transactions, the bits. When two electrons become entangled, it means the binary answers defining their states are linked at the source code level. Their bits are part of a single, unified logical operation. Measuring one particle isn't sending a signal. It's simply querying the cosmic computer and forcing it to resolve a specific line of code, which instantly updates the correlated entry for its partner. The spooky action is the instantaneous consistency check of a perfectly synchronized database. This framework transforms our deepest questions about reality. The Big Bang was not an explosion of matter in a void, but the initial boot-up sequence, the first cosmic bit being set. The laws of physics are not mysterious decrees written in math. They are the immutable algorithms this universal computer follows, the software of existence. Even the flow of time could be seen as the sequential processing of these informational operations, one Planck scale tick at a time. In such a universe, the purpose of entanglement is computational power. It is what allows the cosmos to be a quantum computer rather than a simple classical one. Classical bits, simple on or off switches, can only process information in a linear, step-by-step fashion. But entangled qubits, through superposition and correlation, can perform vast numbers of calculations simultaneously. This quantum parallelism is the secret sauce that could generate the staggering complexity of our universe from a set of relatively simple underlying rules. Yet the rich, tangible, physical world of galaxies, oceans, and life literally emerges from the ceaseless, silent churn of quantum information processing. The digital physics perspective offers a cold, clean resolution to the mystery. There is no ghost in the machine, only the machine itself executing its code. The beauty and the terror of this idea lie in its reduction. It suggests that at its heart, reality is logical, discrete, and perhaps even comprehensible in its entirety, if only we could read the program. Yet it leaves us with a haunting, recursive question. If the universe is a quantum computer, who or what is the programmer, and on what substrate, in what greater reality, is that cosmic computer running? The programmer's question echoes into the void, unanswered by digital physics, yet it points toward a final, synthesizing vision that gathers every thread we have followed. If we step back from the multitude of explanations, a common pattern begins to shimmer through them all. From the transactional handshake to the holographic weave, from the quantum graph to the conscious hum, a single theme insists on being heard. The universe is not a collection of separate things. It is a vast, dynamic, and ever-changing network of relationships. This is not merely another theory to place on the list. It is the potential conclusion that all the others have been hinting at, the grand, speculative destination of our 30-journey search. In this ultimate view, quantum entanglement is not a puzzling phenomenon to be explained away by a deeper reality. It is the deeper reality. It is the primary currency of connection, the fundamental substance from which everything else is minted. Think of reality not as a stage with actors, but as the play itself. The actors, the props, the stage, these are all temporary roles emerging from the script, the relationships between the characters. In our universe, the particles we call electrons and quarks are not the fundamental actors. They are stable, persistent patterns in an underlying network of quantum correlations. Their properties, mass, charge, spin, are not inherent labels, but definitions that only make sense in relation to other nodes in the web. A particle is what it is because of how it connects. Even the force of gravity, in this relational view, loses its primacy. It becomes a story told by the geometry of the network, a collective effect of countless relational threads straining under the weight of information. Spacetime itself is demoted from a fundamental container to a useful, emergent map. The distance between 2 points is not a pre-existing measurement. It is a description of the minimum number of relational steps, the entanglement bonds, you must traverse to get from one to the other. Empty space is simply the calm, low-energy state of this network, humming with potential connections. This turns our entire understanding inside out. We are accustomed to asking, what is this thing made of? We break objects down into molecules, then atoms, then particles, searching for the ultimate building block. The relational network theory suggests this is the wrong pursuit. There is no final, solitary brick. There is only the mortar, the relationship itself. Asking what an electron is made of is like asking what a knot is made of. The knot isn't made of rope fiber. It is a specific configuration of relationships within the rope. The electron is a specific, stable knot in the quantum network of the universe. Its solidity is an illusion of persistence. a pattern that maintains itself through constant dynamic exchange with the web around it. So, what would a theory of everything based on this principle look like? It would not be a single, triumphant equation that outputs the properties of all particles. It would be a set of rules governing how relationships form, change, and stabilize. The mathematics would not describe objects moving through space and time. It would describe the evolution of a graph, the flow of information and correlation through a network. The laws of physics as we know them, from Newton's apple to Einstein's curved spacetime, would be approximate, large-scale stories that work incredibly well when you have trillions upon trillions of these relational nodes interacting in stable, repeating patterns. They are the classical statistics that emerge from the quantum sociology of the cosmos. In this grand synthesis, every theory we have explored finds a new home. The Copenhagen interpretation's wave function becomes a description of potential relationships. The many worlds branching is the network exploring all possible relational configurations. Pilot waves are dynamic ripples across the web's connections. The holographic principle is the ultimate expression of relational encoding, where the interior is completely defined by relationships on the boundary. Even consciousness from this vantage could be seen as the network achieving a certain level of self-reference, a complex knot of relationships becoming aware of its own existence within the greater web. This vision offers a profound and humbling unity. It suggests that the spooky action that began our journey is not an anomaly, it is the heartbeat of reality. The feeling of separateness you have from the screen in front of you, from the distant stars, is a powerful and necessary illusion generated by your particular location within the network, your specific set of entangled relationships. But at the most fundamental level, the connections are always there, whispering. The universe is not a place where things happen. It is a happening itself, a ceaseless dance of correlation and connection. And we, in every thought and observation, are not outside spectators of this dance. We are the dance, momentarily aware of its own breathtaking, entangled beauty. 30 distinct visions of reality, each offering a key to the same impossible lock. We have wandered from the pragmatic silence of Copenhagen to the infinite branching of many worlds, surfed the hidden waves of pilot theory, and witnessed the spontaneous collapse of reality itself. We have seen entanglement cast as a cosmic hologram, a microscopic wormhole, a fossil from the Big Bang, and even the foundation of time's arrow. We have considered it as a trick of consciousness, a line of cosmic code, and the basic thread from which space itself is woven. This is not merely a list of explanations for a strange laboratory result. It is a map of human imagination confronting its greatest challenge. The persistent, undeniable magic of quantum entanglement has forced us to question everything we thought we knew about what is real, what is separate, and what it means to be connected. It is more than a physics problem, it is a profound window. Through it, we glimpse a universe that might be a single, breathing computation, a timeless negotiation, or a conscious tapestry of experience. Each theory, in its own way, tries to heal the fracture between the weird quantum world and the solid, classical reality we experience. In doing so, they reveal that the fracture might be within our own understanding. The mystery of entanglement pushes us to the edge of science and into the realms of philosophy and wonder. It asks us to let go of comfortable intuitions and embrace a cosmos that is far stranger, more interconnected, and more beautiful than we ever dreamed. So, which of these 30 keys feels like it might turn the lock for you? Does the cosmic hologram resonate, or does the timeless transaction feel more complete? Perhaps you find the elegant despair of superdeterminism compelling, or the revolutionary promise of emergent gravity. Share your thoughts in the comments below. This conversation is just beginning. If journeys to the edge of understanding fuel your curiosity, subscribe for more deep dives into the mysteries of space, time, and reality. Keep questioning, keep wondering, and never stop looking for the threads that connect us all to the vast, entangled cosmos.